Just to illustrate a few things on increasing, decreasing functions, monotonicity, etc. Some functional inequalities can come in very handy, can be proved very easily using the concept of monotonicity. A very popular functional inequality is the following. If x belongs to 0 to pi by 2, and if sin x, we want to show that sin x less than x less than tan x in this interval. For x belongs to 0 to pi by 2, I want to show that sin x would be less than x less than tan x. The way to deal with these inequalities is, suppose I want to deal with this part of the inequality. I construct a function which is difference of these two sides, either x minus sin x or sin x minus x, which this function I am going to refer to as an auxiliary function henceforth, right? So I construct a function fx, which is, say, x minus sin x. Right? Now, what is f dashed x? F dashed x is going to be 1 minus cos x. In the interval 0 to pi by 2, this is greater than 0. This is greater than 0. If f dashed x is greater than 0, fx must be an increasing function of x. Fx must be an increasing function of x. Now, if a function increases, then for x1 greater than x2, f of x1 will be greater than f of x2. F of x1 will be greater than f of x2 if a function increases, right? That means, now in this interval x greater than 0, x1 greater than x2, so f of x1 will be greater than f of x2. So this would mean f of x will be greater than f of 0. F of x will be greater than f of 0. Hey, but what is f of 0? F of 0 is 0, as you can see. F of 0 is 0, as you can see. So which means this gives us fx greater than 0. Fx greater than 0 means x minus sin x greater than 0, x greater than sin x, right? Right? That's this part of the inequality, sin x less than x. Let me look at the next part of the inequality, x less than tan x, x less than tan x. Clear? Clear? Say this part of the inequality, x less than tan x, for x belonging to 0 to pi by 2. Again, construct a function, say phi x, which is, say, tan x minus x, right? What is phi dashed x? Sec squared x minus 1, which is tan squared x, which is greater than 0 in the interval 0 to pi by 2, right? That means phi dashed x positive means phi x must be an increasing function of x, right? That means for x1 greater than x2, phi x1 will be greater than phi x2. This is what it means, right? So for x greater than 0, x1 greater than x2, phi x will be greater than phi 0. But what is phi 0? Phi 0 is 0, as you can see. Or tan x minus x greater than 0. Clear? Tan x minus x greater than 0. This is what it means. So tan x greater than x. Let me look at a few more inequalities. Can I wipe this off? Say for x greater than 0, x must be greater than ln 1 plus x. For x greater than 0, x must be greater than ln 1 plus x. Again, let me construct a function fx, which is x minus ln 1 plus x. Right? Examine its monotonicity, increasing, decreasing trend, differentiate. F dash x is 1 minus 1 by 1 plus x, which is like x by 1 plus x. X is greater than 0, so this is greater than 0. So if f dash x is greater than 0, it means that fx must be an increasing function of x. Fx must be an increasing function of x, yes or no? Right? That means for x greater than 0, x1 greater than x2, fx1 will be greater than fx2. That means fx must be greater than f0. This is what it means. But what is f0? F0, as you can see, is 0, right? So fx is greater than 0. Fx greater than 0 means x minus ln 1 plus x will be greater than 0. X therefore will be greater than ln 1 plus x, right? Now, can I wipe this off? Let me look at a few more inequalities. Say for x greater than 0, e power x greater than 1 plus x. I want to show for x greater than 0, e power x greater than 1 plus x. Construct an auxiliary function fx, which is e power x minus 1 plus x. Right? Examine monotonicity, examine increasing, decreasing, differentiate with respect to x. But for x greater than 0, e power x will be greater than 1. For x greater than 0, e power x will be greater than 1. Yes or no? Will be greater than e power 0. So greater than 1, right? So e power x minus 1 will be positive. So f dash x greater than 0 means fx must be an increasing function of x. Right? So for x greater than 0, fx will be greater than f0. Fx will be greater than f0, right? But what is f0? 0, as you can see, right? So e power x minus 1 plus x greater than 0, e power x therefore will be greater than 1 plus x. Let me illustrate a little more. Can I wipe this off? Say for x belonging to 0 to 1, x belonging to 0 to 1, tan inverse x is greater than x minus x cube by 3 less than x minus x cube by 6. Tan inverse x greater than x minus x cube by 3 less than x minus x cube by 6. Let me look at this minus this to establish this part of the inequality. Let me construct an auxiliary function fx, which is tan inverse x minus x cubed by 3. Right? F dashed x would be 1 by 1 plus x squared minus 1 minus x squared. Right? Which is like x squared minus x squared by 1 plus x squared. This minus this is minus x squared by 1 plus x squared, and this plus x squared. Right? So which is like x power 4 by 1 plus x squared. Isn't it? Which is greater than 0, as you can see. So which means f dash x greater than 0 means fx must be an increasing function of x. Fx increasing function of x means, Diptesh, for x greater than 0, fx will be greater than f0. For x greater than 0, fx must be greater than f0. But what is f0? f0, as you can see, is 0. Fx greater than 0 is what turns out to be. That means this minus this is greater than 0. This will be greater than this. Clear? Let me examine the next part of this inequality. This one. Let me construct a function phi x, which is x minus x cubed by 6 minus tan inverse x. Right? Phi dashed x 1 minus x squared by 2 minus 1 by 1 plus x squared. Yes or no? This minus this I can write as x squared by 1 plus x squared minus x squared by 2 yes or no? I could take x squared common from this. 1 minus x squared by 2 into 1 plus x squared. But x lies in the interval 0 to 1. So 1 minus x squared will be positive. So all of this will be positive. Right? So phi dashed x turns out to be positive. So phi x must be an increasing function of x. Right? And therefore, for x greater than 0, phi x will be greater than phi 0. But what is phi 0? Phi 0, as you can see, is 0. So phi x will be greater than 0, etc. Right? Let me illustrate a little more. Can I wipe this off? Say, in the interval 0 to pi by 2, sin x is greater than x minus x cubed by 6. Say in the interval 0 to pi by 2, sin x greater than x minus x cubed by 6. See, let me construct a function which is phi x sin x minus x cube by 6. Right? Phi dashed x is cos x minus 1 minus x square by 2. Yes or no? Right? Which is x square by 2 minus 1 minus cos x square by 2 minus 1 minus cos x. Yes or no? Now, phi dashed x still does not come up with a sign unambiguously. What I do is I differentiate a second time. Phi double dashed x is what? X minus sin x. X minus sin x. Hey, but we've proved that x is greater than sin x in the interval 0 to pi by 2. We proved that x is greater than sin x in the interval 0 to pi by 2. So this is greater than 0. If phi double dashed x is positive, that means phi dashed x must be an increasing function of x. Yes or no? This is a certain function and this is its derivative. If the derivative is greater than 0, then this function must be an increasing function of x. Phi dashed x itself must be an increasing function of x, which means phi dashed x is an increasing function of x. That means for x greater than 0, phi dashed x must be greater than phi dashed 0. Since phi dashed is an increasing function of x, so for x greater than 0, phi dashed x must be greater than phi dashed 0. Right? But what is phi dashed 0? 0, as you can see, phi dashed 0 is 0. Yes or no? Which means phi dashed x turns out to be greater than 0. If phi dashed x is greater than 0, phi x must be an increasing function of x. And if phi x is an increasing function of x, then for x greater than 0, phi x will be greater than phi 0. But what is phi 0? Phi 0 is 0, as you can see. This greater than 0 means sin x will be greater than this, the interval 0 to pi by 2. So, you know, this entire business of monotonicity, increasing, decreasing comes in very handy practically, especially if you look at functional inequalities. Then the concept of monotonicity, increasing, decreasing is a very, very useful concept. Let me also tell you another way to look at functional inequalities, that is using graphs. Okay. Can I wipe this off? Say, if x1 and x2 are two real numbers, say x1 and x2 are two real numbers, okay? I want to establish by 3, they are distinct, x1 and x2 are distinct real numbers, say. I want to establish that this is greater than e power 2x1 plus x2 by 3. Right? I want to establish 2 e power x1 plus x2 by 3 is greater than e power 2x1 plus x2 by 3. Yes, AMGM for sure, very nice. I knew someone will come up with this, but I'll now migrate beyond AMGM. AMGM will work wonderfully. E power x1 plus e power x1 plus e power x2 by 3 greater than or equal to the cube root of e power x1 into e power x1 into e power x2. This is readily AMGM, very true, very nice. But let's look at it graphically also. Okay, what I do is, let me draw the graph of the function y is e power x, right? And build up the elements e power x1, e power x2, 2, etc. on the graph of this function. And let's get a visual feel for this inequality, right? Let's get a visual feel for this inequality, all right? This is x1. This length is e power x1, right? This is the graph of y e power x. This is x2, and this length is e power x2. This point has coordinates x1 comma e power x1. This point has coordinates x2 comma e power x2. All right. Now, what we are setting out to prove is 2 e power x1 plus e power x2 by 3 greater than e power 2x1 plus x2 by 3. This is what we set out to prove. Okay. Let me draw a second. This is A, this is B. AB is a second. It will not matter. I mean, one of them has to be larger, the other one. It will not make any difference. You'll see that in a short while. You'll see it's not going to make any difference. I mean, if I replace x1 by x2, then this will become x2 and this will become x1, isn't it? What difference will it make? Now, let me locate this point, 2x1 plus x2 by 3. 2x1 plus x2 by 3 is an x that divides the line joining x1 and x2 in the ratio 1:2. Yes or no? Section formula, right? So there is a point x which is 2x1 plus x2 by 3, and this x is like this is to this is 1:2. That must be this x. Yes or no? Now, this is a point P. This is a point Q. This is a point R. Now, AR is to RB will also be 1:2. This is to this is the same as this is to this. Similar triangles, right? So, y of R would be 1 into y of B plus 2 into y of A divided by 1 plus 2. Yes or no? That's going to be y of R using section formula. Right now. So, y of R using section formula is going to be 2 e power x1 plus e power x2 divided by m plus n, that's y of r. Yes or no? Hey, this part obtained, right? And y of q is e power x of p. Yes or no? This length is e power x. Yes or no? This length is e power x. So y of q is actually e power x, this x, which is like e power 2x1 plus x2 by 3. Hey, which is bigger, y of r or y of q? Y of r is bigger than y of q. Got me? Okay. Let me illustrate a little more using graphs. Suppose x1, x2, x3 are distinct angles of a triangle. Clear? Now, I want to compare these two entities. Sin x1 plus sin x2 plus sin x3 by 3 and sin x1 plus x2 plus x3 by 3. I want to compare these two. I want to find out which of the two is larger. I want to find out which of the two is larger. If x1, x2, x3 are distinct angles of a triangle, whether sin x1 plus sin x2 plus sin x3 by 3 is larger, or sin of x1 plus x2 plus x3 by 3 is larger. Now, the graph of y equal to sin x, of course all these x's will lie in the interval 0 to pi, right? Let me draw the graph of y equal to sin x in the interval 0 to pi. Say this is x1 and this point is some p. This is x2 and say this point is q. This is x3 and say this point is r. Okay. What are the coordinates of P? x1 comma sin x1, isn't it? P is x1 comma sin x1. Q is x2 comma sin x2. R is x3 comma sin x3. Right? These are PQRs. Now, this triangle PQR has a centroid. This G is the centroid of PQR. The x coordinate of G would be x1 plus x2 plus x3 by 3. The y coordinate of the centroid, it would be y1 plus y2 plus y3 by 3. That will be yg. M would be what? Y coordinate of M would be sine of xg. Would be sine of xg, yes or no? Right? Which is bigger, ym or yg? Ym is bigger than yg. Ym is bigger than yg. That means sine ym is sine xg. Xg is what? Xg is x1 plus x2 plus x3 by 3. That's the x coordinate of the centroid, right? So sine of x1 plus x2 plus x3 by 3 will be greater than y of g. Y of g is sine x1 plus sine x2 plus sine x3 by 3. Right? So graphs are quite a handful. Graphs are quite a handful. Once you get acclimatized and kind of addicted to using graphs, you're going to experience bliss. A large number of algebraic manipulations can be dispensed away, or large number of trigonometric hassles can be weeded away, and you'll find that large number of things coming out in such a simplistic manner, and will offer great amount of versatility in obtaining and establishing results. Yes, there is concavity and convexity of curves, which I'm. Yes, yes, that's called Jensen's inequality. Actually, in a very general sense, it's called Jensen's inequality. But yes, it is general for concave and convex curves. I could have said f of x1 plus f of x2 plus f of x3, etc. by n. All of this can be generalized, but again, that generalization will not take place using the graph of this function, because then those graphs could be different. Then the concept of what we refer to as concavity and convexity will come in the picture. But yes, that inequality is called a Jensen's inequality. This is only a special case of Jensen's inequality.